Bien, nous allons commencer. Bonjour à tous. Welcome to all of you to the Séminaire of Laboratoire Jacques-Louis Lyons. We will have the pleasure today to listen to Professor Klemens Fellner, who is with the Institute of Mathematics and Scientific Computing at University of Graz, and who is going to speak reaction diffusion systems about their analysis and large time behavior. So please, Klemens, we listen to you.
Thank you very much for the kind introduction and for the invitation. It's a real pleasure and an honor to speak in this seminar. What I'm going to talk about in some sense has quite a history and a very strong connection to being in Paris and in France. It actually started all with somehow a remark or a question by Laurent de Villette, back then at the ENS Cachan. Did my PhD, I was working on kinetic equations, and then there is this concept of, like something like hypercoercivity. And Laurent was mentioning, okay, if you look to reaction diffusion equations, and you have some like a degeneracy, let's say, in the diffusion, do we have a similar situation of those? And okay, that seemed like a very interesting question. So we started to dig into the topic, and we tried to use sort of methods which we have learned in kinetic theory. And this is the beginning, basically, almost now 20 years ago. Right, the first time I was in Cachan was really April 2003. I'm happy to report that now we have made actually really substantial progress in many of these questions, and I try to sum it up in a kind of easy, memorable way. So I will start with a sort of a specific example as an introduction, sort of, and then tell sort of some cornerstones of the story I try to say. One of it is concepts of entropy, and the other one is like concepts of global in time solutions. Because whenever we are talking about nonlinear problems, you have to ask yourself how long are solutions in existence. Solutions is here already too little to say, because you really have to define actually what kind of solutions you expect, weak or classical ones, or in this game also renormalized ones. So diffusion equations, of course, are one of the most widely used PDE models. Everybody of you knows that. Some very famous models like the Hodgkin-Huxley for nerve signaling. There's a lot of population dynamics or structured populations. There are chemical reaction networks. You have phenomena like pattern formation and Turing instability, which is to do with anything like morphology. And also then very sort of advanced subjects like Belousov-Zamputinsky kind of time oscillatory solutions. And if that would be a bit of a different talk, I could tell a lot about the process which is called lipolysis, which is basically how the body is providing fatty acids for the metabolism. So this is be it for energy or be it for construction of new cells. And there is a typical example like that. But for today, I'm going to take an example actually which goes back all the way to the time being with Laurent, maybe not 2003, maybe it was 2004. It was a kind of a system where four species react to each other. So here the species should be a 1 and a 2 and a 3 and a 4. And you have one reverse. This could be an example for instance, do you see my mouse if I go around?
Yes, we can see it perfectly.
So that would be a silver nitrate, natrium chloride reacting to silver chloride and natrium nitrate, basically. That would be an anorganic example for that. But in organic chemistry, and this refers back to this lipolysis up there, because there it's a big role, all kind of reactions which are called esterification might have a similar scheme. And so why do I choose this particular example? Well, there are multiple reasons for that. The first one, it has detailed balance condition. It's just one reversible reaction. So there is this micro-reversibility. And this is a structural property which is going to be good for us. In particular, in order to sort of translate this reaction scheme into mathematical equations, we are going to use the simplest possible thing, which is called the mass action law. And then you have certain reaction rates, gain and the loss term. And in terms of, the diffusion, suppose that you're in a bounded, nice enough, smooth enough domain, and you find the mass you have there by homogeneous Neumann boundary conditions, so there is no in and out flux for the sake of clarity. What you then have is a system of parabolic equations, all of which have some sort of a heat equation term on the left-hand side and reactions term on the right-hand side. And with this kind of structure of having these four species, two of them forming two other ones, all of the reaction rate terms are sort of quadratic. So that's the nonlinearity is sort of distributed evenly on the reaction terms. And this makes it like a complete structure of equal difficulty in all of the reaction terms which are present. And on the left-hand side, there is no reason to assume that the diffusion coefficient of the species should be the same. So what you should assume is that the diffusivities are different. And then all of a sudden, this system loses a lot of the sort of formal properties which you are remembering from a heat equation. Like a comparison principle which gives you a priori estimates does not hold for such a system. Okay, if it would be the same diffusion coefficient everywhere, then it would hold. If you have a very particular right-hand side structure which has a certain monotonicity property, then you find maybe a maximum principle or something like invariant regions, which give you basically a priori estimates. But this is all of these special cases which have been treated already back in the 70s, 80s very well, if you look into the book of small classical textbooks on reaction diffusion equations. But this is not the case here. And in particular, if you want to think about bypassing this sort of structure, if you think of maybe gaining some regularity about knowing classical solutions, there is no weakness on the right-hand side, no lower order term which would be natural to start the bootstrap with in order to gain regularity. That has also been done tremendously in all of this 80s, 90s literature. So there is none of these tricks which somehow connects a system of reaction diffusion equations to, let's say, a heat equation or some of these things which you know from a parabolic equation. At this point, it's actually not even clear if there couldn't be something like Turing instability, which means that if you look at the ODE system and you have a clear stationary state, which you have in this case, it might be that by adding diffusion to it with sufficiently different diffusion coefficients, this sort of homogeneous stationary state is not stable anymore on the heterogeneous level. It might be that there are peptides emerging, which are actually forming then a stable stationary state, rather than having a homogeneous stationary state, which also the PDE system should be subject to, because with this kind of homogeneous Neumann boundary conditions, in the end, everything should diffuse to a constant, and sort of the PDE dynamic should reduce to an ODE dynamic in some sense. So this is where we started and thought, okay, what can we understand about this with, like the methods which we have learned? And actually, I should probably even motivate why we were thinking about the methods we have learned in kinetic equation, because this system inherits Boltzmann's entropy. So this was done formally by Laurent and Marcia Abisi, that if you have a system of basically 5 reactive Boltzmann equations, one of them reduces to kind of an omniscient background who is in equilibrium, then exactly this is the macroscopic limit. So that's also reassuring that in sort of a thermodynamical sense, it's not the formulation of the system which is flawed in order to maybe give you mathematical difficulties. This is indeed the proper thermodynamically correct model within a certain asymptotic range of certain reactions. And the kinetic entropy, which we all know very well from kinetic theory, is the Boltzmann equation. It's the logarithmic entropy density, and it's actually a free energy functional. And basically back then, since we always used sort of, when we have an entropy functional, right, then you can calculate the entropy dissipation. So actually dissipation, one should be careful with. Dissipation is the expression knowing that it's an energy functional. Why, if you only know that it's an entropy functional, you should rather use the term entropy production, because entropy is produced in the literature of thermodynamics, at least in some parts of the literature. And so therefore, that would be the more proper way to use entropy production, but obviously the letter D, which is formed here, refers to the dissipation of the free energy. And the story which this entropy dissipation tells you is expressed in the form of the dissipation functional, which you can easily calculate, right? It has two terms. It sums up two terms, both of which are non-negative. So when you ask when does the entropy dissipation stop, both of them have to be zero. The first term is just the Fisher information. If you expand basically the gradient, you have what you have there basically as a Fisher information, and it drives that all of the concentrations should be homogeneous in space. Okay, and that's already a killer against having something like a Turing instability, because any heterogeneous space could not be a minimizer of the entropy. And the second term is basically balancing all of the reaction rates, and this is really looking like the Boltzmann inequality, right? So it really forces you that basically this expression is zero. So, and this sort of link to kinetic theory was the one where we wanted to understand, okay, what knowing all of the sort of ideas of kinetic theory, like entropy methods and other things, what can we infer for that for two basic questions of the analysis of this kind of systems? The question of global existence of different types of solutions, and in which sense do you converge to the equilibrium stage, which should be defined basically by a minimizer of the entropy. Well, let's have a look what it is. I mean, I already mentioned here, okay, equilibrium state should be space homogeneous and it should balance the reaction. But, you know, if you basically have that, then you have for these four species, which in equilibrium will be constant concentrations. So for four constants, you at this point have only one equation. And this doesn't really give you a unique equilibrium. So in which sense do you have something like a unique equilibrium? Well, in the sense that you have to remember all of the mass conservation laws, because in these kind of reactions, of course, we never have the loss of mass. There's no nuclear reaction going on which transforms mass into energy. In the basic chemistry book building of stoichiometric sort of laws, there is certain conservation laws. And in this particular system, you can actually show that there are three which are linear independent. And you choose your favorite three. You calculate the initial mass which you have, and then have all of a sudden three more constraints. And this is a very general theory, which you can read in lecture notes of Martin Feinberg, goes back to 72, Jackson and Horn, that basically there is quite a general theory about the uniqueness of equilibria for reaction networks, for chemical reaction networks. And this is just a special part of it, so that there is, once you have given the initial masses, then you have for the given initial masses a unique equilibrium state. Of course, if you change the initial masses, then the equilibrium state might change as well. And in that sense, we can try to explore a bit more the entire idea of having an entropy. And this was done with the methods we've sort of been studying in kinetic equations, which is called roughly the entropy method. You observe that you have like a convex entropy functional, you have some sort of entropy dissipation, and an equilibrium state, which is entropy minimizing. And you have a law of how the entropy, actually more precisely, you want to look at the distance of the entropy to the equilibrium entropy, which is then called often a relative entropy, that is maybe the better object to look at, that dissipates, right? And if you then can translate this equality that entropy dissipation is zero exactly when you're in equilibrium, if you can translate this equality into a functional inequality, which measures the entropy dissipation down by some function to the relative entropy, then you get explicit convergence first in this relative entropy, but the relative entropy with some Zizek-Kuhlbach-Pinsky inequality gives you a control of the L1 norm. So then also in classical L1 norm. And the example before should remind you that what you have to take into account in this process for sure is all of the conservation laws. Because that's the one which here even allows you to identify the right equilibrium. So it cannot be that you can neglect the conservation laws of the system. They are necessary to identify the right equilibrium which you want to converge to as an entropy minimizing state. So In kinetic equations, this was sort of an idea which went even back to Boltzmann and Grad, and then it was used for like all kind of nonlinear diffusion equations, porous media equation, going back to Toscani or the seminal papers of Carrillo, Jüngel, Markovic, Toscani, Unterreiter, Arnold, Markovic, Toscani, Runkeweiter. It was extended by De Villet and Villani, for instance, with the view of doing the big shot, which was looking at Boltzmann equation and formally showing that the equilibrization of smooth enough solutions of Boltzmann equation would occur much faster than the Poincaré recurrent theorem. So that's what this entropy method is capable of. It's based on functional inequalities and not on particular solution along estimates along solutions. It avoids linearization, so it gives you global results, and it even allows for explicit constants in order to be sure how you converge. So for this direction diffusion equations, we were actually sort of trying to build up a theory how to do this, which was quite different to the one which was used in the previous literature. There was always something like a Bakri-Emery strategy, which was used for porous media, and there it works quite well. But nobody ever managed to get Bakri-Emery working for systems. The amount of terms occurring is so many that Bakri-Emery basically was such a mess that nobody understood if it can be done. It's just impossible. So we had to come up with an entire different way of doing things, and this took several papers. We started with smaller system and learned more, and then from 2008 on, we had basically an idea how to do this system quite well, and then with a significant improvement. And then there was more structural theory added, a lot by Alex Milke. In the end, what you can do now quite well for this system is that you really can estimate the entropy dissipation of our particular system in terms of, that's a different notation for the relative entropy, but this is again the relative entropy, and then some constants which depends on the initial masses. These constants are not sharp, so we are not having sharp results, but we have captured easily exponential decay, and this is a nice thing to do. In fact, if you are interested in how to do that, I think the most general result currently was written up in 2018 in XAMPP, together with Bao Tang, where we basically show that we can extend all of this knowledge to complex Bell-length networks, so arbitrary large networks, which still have something like a nice entropy structure. And even we don't even need to know if there are weak solutions. It works for renormalized solutions. And so it's basically any system which has some sort of meaningful structure like this will converge to equilibrium. Even if the solution you have is just as poor as a renormalized solution, it will go to the equilibrium state. Right. The way how to do this, just for the people which might not have seen it, which I think are not very many, I mean, all what you do with this entropy inequality, which you have here, if you have the change of the relative entropy is an entropy dissipation, and you have this inequality, you just use it, you use a Gronwall argument, and there you've got it. That's all it is to it. So in fact, the difficulty of the method is really not in doing the Gronwall argument, it's in definitely improving this inequality, and this can be very, very technical, so I'm not going to say anything about this at the moment. But it leaves you basically with this one understanding, okay, in the sense of L1, pretty much for any system with as large as nonlinearities you imagine, polynomially nonlinearities of arbitrary order, as long as you have this thermodynamical structure, you will converge exponentially to the equilibrium state. And that's nice because that also means that you have something like L1 or pre-estimates. But in order to have, let's say, classical solution exists, what you would need to have is let's say, L infinity a priori estimates. I mean, L infinity is not quite necessary. You can do with a little bit less. But let's say if you manage somehow to get L infinity, then of course you can continue to use all of your favorite arguments and find classical solutions, right? So there is, in principle, the gap between L1, which comes from the, let's say, the general entropy structure, and sufficiently large LP, or let's call it L infinity norm information, in order to kill the nonlinearities on the right-hand side. and be able to extend solutions local to global in time solutions. So what we have here is a kind of a conundrum, right? Here we have convergence in the sense of L1, but the equilibrium state is actually constant. So this is C infinity states. So we have here something which is, you know, kind of whatever sort of weak solutions, or maybe even a renormalized solution, that converge in L1 to C infinity solutions. So what can this help us somehow? Well, from the pure entropy structure, you actually really don't get very much in the terms of a priori estimates. I mean, what you use for Boltzmann equation is that, for instance, the entropy has a sign, right? Entropy dissipation as well. So you have a priori estimate of the entropy at a certain time in terms of the initial data because you have a sign. And you have a priori estimate for the time integral of the entropy dissipation. If you then translate into sort of spaces, it means that from the bounds on the entropy, you have something like L infinity in time and L log L in space. And from the entropy dissipation using the Fisher information, you have something like that the square root of the concentration is L2 in time, H1 in space. So this is what you get from the entropy structure. And of course, you know, like here we have a higher time integrability, here we have a higher space integrability. So you can interpolate, and depending on the space dimension, you get the following outcome. In 1D, you immediately get something like almost L3 integrability in space and time. So if you then use a parabolic bootstrap, you actually just bootstrap a few times and you have global classical solutions. Beautiful. But already in 2D, if you try to use this a priori estimates only, you can still just use true linear inequality, which is the H1 embedding in 2D in terms of this exponential function and then some sort of a Lagrange dual function, which is involving then the logarithm. And this just works out that this a priori estimates give you a L2 bound. So you have a global L2 bound, but the L2 say that you can pass to an approximation limit very easily. So if you do that in the first way, you actually get, instead of weak L2 solutions, you get only super solutions, and then you have to work on those with a lot of very sophisticated theory hailed to Michel Pierre and co-workers. You know that there's actually global weak solutions in 2D. But this has been using very borderline sort of techniques in terms of integrability. And already in the physical 3D space, if you just use this, you don't even get this this kind of integrability. All you get are renormalized solutions, which we proved back then with Michel Pierre and Julien Bouvet and Laurent, and was sort of a bit of the first result in terms of these renormalized solutions. In particular, Julian Fischer then later proved global renormalized solutions for very, very general mass action law systems. So the entropy alone is not the killer application in terms of reaction diffusion equations. Okay, for kinetic equations, admittedly, you don't really have much, and that's why we have what we have. But for reaction diffusion equations, it doesn't give you that much as you would like to have. So there comes argument into the game, which is called the duality argument, and is specific to this kind of elliptic and parabolic structures, which I also would like to sort of sketch briefly. Basically, it is the following idea. So let's start with the last equation here. If you were to sum up our system from before, then the right-hand side is basically 0. Okay, this is the conservation of the total mass which you have in our particular system, because it's just the reversible reaction of this into that. But you can improve on just using summing up the concentrations by summing up the Boltzmann densities, right? And then what you have is not the conservation law, but somehow the structure of the entropy dissipativeness, which gives you at least a sign on the right-hand side. And so you have a summation of the entropy densities of our systems giving you that thing. Okay. At this point, there seems to be no reason why to do that at all. I mean, if you consider the sum of the concentrations of a new variable, it's not a closed system for this new variable, because here you factor in the different diffusion coefficients. So this is one point where you see that different diffusion coefficients are formally a very different game then the same diffusion coefficients, because it would be the same, you could factor it out, and you have here a closed system for which you can use heat estimates, right? But in general way, you can't. So, we all mathematicians, if there is something we don't have, we can at least try to force it to look that way, right? So we could pretend that, this sum of the entropy densities is a new variable, and we can forcefully rewrite this sum, which is here, as some coefficient m times this new variable. And this m is then the sum of the di zi divided by the sum of the zi, and this has a particular structure. In particular, it is bounded above and below independent of the ingredients. So it's bounded above by the maximum of the diffusion coefficients and bounded below by the minimum of the diffusion coefficients. So this coefficient is always bounded in L infinity and below by something like the minimum. And that's the point where the idea of the duality argument sort of comes in. Imagine you have now this artificial system with such a coefficient m. I'm just showing the simplest case where you have a lower bound, but this can be generalized. So what I do with this dissipative structure, you define yourself a proper dual problem. And the dual problem goes backwards in time. So instead of having a forward in time, you have a backward in time. You change this coefficient outside of the Laplacian, like you were to do calculating a joint operator. And you sort of force it with an arbitrary non-negative right-hand side. And in order to make it a nice well-posed problem, actually you make it an end-time problem. So you impose that at the end time t, which is arbitrary but fixed for this argument, this solution of the dual problem should be 0. And you also impose the same boundary conditions like the forward problem, let's call it this way. So what happens now if we test the dual problem with the solution? So we basically multiply here with z, the solution of this sort of inequality, and integrate over space and time. Then we have this integral at the one-hand side. At the other side, we multiply wt with z, integrate by parts. So we get boundary terms in time. The one at capital time t is 0. So there is only the boundary terms in time at 0. And then you have basically now the integrated wzt. The wzt is that t satisfies this inequality. You have done the proper jointness of how you define the argument here. And so see that actually these two terms cancel away. And so this is all which you have here, the inequality translating from here to here. And if you then know that this is some like a dual problem, which is n time, you can actually sort of exchange the time direction to see this is a normal parabolic equation. And you have a pre-estimate basically of the solution at the time 0 in terms of the forcing of the right-hand side. And so this L2 scalar product, which you have here between the solution to be understood and this sort of test function is bounded in terms at the solution to be understood at time 0 measured in L2 and the L2 norm of the test function. And so therefore, by duality, since this is for arbitrary test functions, you have learned that there must be a constant such the L2 norm in space and time of this solution is bounded in terms of its initial data at time 0. And this constant is something which depends polynomially on time, which can be interesting. So the idea of this duality estimate was very nicely summed up in a review by Michel Pierre, but goes back much earlier. It was part of this literature 80s. In fact, I don't even know where there is the first reference to it. That nobody seems to know, not even Michel Pierre, but it's a beautiful argument. And it gives you basically, in our context, global in time estimates, which are just L2. But since we use the entropy density, remember entropy density includes also this logarithmic term, it's L2 log L squared. So, and if you have this L2 log L squared and you have quadratic nonlinearities like for our system here, you immediately get some uniform integrability of the nonlinearities. So it's a very easy argument to pass the limit in an approximated sequence of classical solutions, and you have global L2 weak solutions in all space dimensions. So that's a nice improvement, which you can generalize in many different ways, but I'm sort of skipping that. In fact, you can do even a bit better. This was something which Laurent, Jose Alfredo, and myself did somewhat later. If you look carefully at the structure, you can get, instead of L2, something which is a little bit better than L2, depending on space dimension and some conditions. So if you do that, and I try to be a bit fast here, skipping a few technical details, what you can actually do then in 2 space dimension, you can use this slight improvement to be sure that there always is a bootstrap, that these weak solutions, which are a little bit better than L2, with a bootstrap are actually becoming classical solutions. In higher space dimension, there might be a gap. So in higher space dimension, I'm skipping the technical details. In higher space dimensions, you might need a condition basically that the diffusion coefficients are not quite different, something like this here. So if the diffusion coefficients are not too different from each other, depending on the space dimension and some sort of structural constants, then you can also get classical solutions out of the weak solutions, but this is not the general theory with this argument. So this is where I wanted to make my first sort of summary point. So because that is sort of the state of the art until recently, the entropy structure is beautiful. It's beautiful in the sense that it makes you understand very well how you converge to the equilibrium, but it's not very powerful in the terms of giving you classical solutions, global in time classical solutions. In 1D, it works, but in 1D, this was also well known already back to Arman with methods and so forth. In 2D, we got this improved duality method classical solutions. And that sort of was a simplification of a first result in that direction for this particular system by Goudon and Vasseur. Goudon and Vasseur used the George's method, particular for this system, quite technical in order to have global classical solutions in 2D. But for any higher dimensions, like even the physical space 3D, classical solutions in general were still unknown. We had global weak solutions. We knew then those converge exponentially to let's say, to the equilibrium in sufficiently small LP space. No general classical theory. So that connects to the question, can you even expect a general theory? Or for what kind of system might you expect it? And there was a very, very famous counterexample by Michel Pierre and Didier Schmidt, that for a system which you thought it satisfies the nice structure, there might be finite time blow up. And what is the nice structure? The nice structure is it's positivity preserving. Why? Because we are modeling some concentration. So it should be non-negative initial data should have non-negative solutions, right? It's positivity preserving, and there is some sort of a mass control, conservation law. So if you have these 2 problems in an ODE setting, right, and you think of anything, then the ODE setting immediately gives you global classical, as a global in time solutions. But for the PD setting, since this is only entailing a L1 conservation law, L1 is not enough to be sure of global classical solutions. In fact, Michel Pierre and Didier Schmidt constructed a counterexamples where with these 2 properties, you would have a global, L1 bound, but for large enough LP norms, you have a finite time blow-up. So what can you do? I always felt it very unsatisfactory whenever I imagined to talk to chemists what the theory of chemical reaction networks is, that for even that particular system, we have no way of arguing that there are global in-time classical solutions in the physical space. Nobody would expect anything to happen for that system, of course, but that we can't show it is something which is not satisfactory, right? So luckily, we're able to improve these situations in the last years, basically to almost as far as you would like to have it. So imagine now a general reaction diffusion system with some diagonal diffusions. We're not talking cross diffusion, which is a different ballgame. But we have a nice sort of system. Again, mass is confined in a domain, which is either the whole space or a smooth enough domain to avoid technical problems. You have L infinity initial date, and you have these nice sort of structures. Of course, you have quasi-positivity, which is non-negative initial data will cause non-negative solutions. You have smooth enough, like you're used to them, local Lipschitz containers, and you have a mass control. So if you sum up direction terms, then it's maybe not bounded by zero, like when you have mass conservation, but it's bounded above in something which is most a linear growth. Okay, so if you have something which is at most a linear growth, this is what we call mass control. And then if you have that the individual reaction rates are growing not faster than sort of quadratically, where you can actually generalize quadratic to slightly super quadratic. So depending on the space dimension, there should be a positive epsilon where this is still true. Then you have global classical solutions, okay, in all space dimensions. So in fact, the argument which we used in order to prove that has its root in a paper of Canel, which was mostly forgotten in the 90s, which sort of was then unearthed. Actually, you know, I think in the end, the one which really the first time looked into it was Bau, and he had to use a Russian colleague of ours in order to get sort of the Russian paper a bit understandable, and then finally we found something better. It is sort of the end of a development which was first published by Caputo, Goudon, Vasseur, which sort of maybe had the same result, but also used the entropy condition. So on top of these conditions, they used an entropy condition. And then Souplé, actually, after the preprint of Caputo, Goudon, Vasseur, published an improvement, still using the entropy condition, but simplifying some of the technical arguments by using smart semi-group estimates. A paper was actually published even then earlier than the Caputo, Goudon, Vasseur, but those were the first one to show classical solutions. Yet all of these results here, 19 and 18, Caputo, Goudon, Vasseur, and Souplé used an entropy condition. This we were able to drop. Actually, Goudon, Vasseur, Caputo thought in the paper already that they expect that the entropy condition might not be crucial, and one probably can drop it. But with their Di-Giorgi kind of estimates, there was no way to do that. And even Souplé with his improvements couldn't drop it. So this result was then published in the Annals of IHP in 2020, and it's an enormous improvement in terms of existence theory, because all of a sudden we are not embarrassed about not knowing classical solutions in 3D anymore. It has some basically more add-ons that, depending on how the mass control is, you might, so if you have mass conservation, you basically grow at most polynomial in time, and if you have some mass dissipation, you have an inherent convergent to zero, because then the mass dissipates to zero, so in the end everything is zero. So I'm not going to go into details of the proof, because that's quite a remarkable feat of rewriting things and observing things. I just want to point out at some point, in order to really get these classical solutions, you do need a regularity result, which says that if you have a solution to the heat equation, so you already have solutions, and this solution, for some reason, whatever, satisfies a particular Hölder continuity and some upper bounds, then there is a type of gradient estimate which you get in terms of these constants of these upper bounds. So this is basically, okay, there exists already a solution, and if it satisfies these kind of constraints, then we have a particular gradient estimate. And now at this point, it seems completely strange why a regularity lemma for the heat equation should help us with our global existence for the systems, when I originally said somehow that the systems just don't behave like the heat equation. Otherwise, the theory would be much simpler. And this is where the magic happens. It somehow is possible to sort of put things apart in a smart way and sort of split sort of regularity theory and other arguments. So just have a look at this sort of thing. One of the ingredients, and I'm really not telling you where it pops up, all of a sudden has some sort of a generalized parabolic equation with a coefficient now, which is again sort of satisfying similar upper and lower bounds like we have seen for the duality estimate. And this helps you to obtain a certain type of Hölder regularity. And this Hölder regularity is crucial. And so in the end of the day, you can which wins you the day. And this is quite remarkable, You can even improve it and get uniform in time bounds and not just global existence. This was done sort of in a special issue for Michel Pierre. And this is really a sort of a much more general existence result than it was available remotely before, because it applies to many of these problems. And even more recently, there is a preprint out by Michel Pierre and Didier Schmidt again, where they sort of prove that the result here is more essentially optimal. They prove examples with finite time blowup, where for any super quadratic exponent, you find a space dimension which is large enough that a particular 2x2 positivity mass dissipative system, so mass dissipation is even sort of more strict than mass control, right? Because here basically the mass goes really down or is conserved, features a finite time blowup. Blowup in the sense that the L infinity norm becomes unbounded. And so there is really not much to do better than we have done. I mean, the exact value for, let's say, for a particular space dimension, where is really the value where you have still global solutions and where you have blowup, that is not determined. But basically, you know, we have proven that for any space dimension, there is a positive epsilon, so that for corresponding super quadratic systems, you have global in time solutions under the assumption of positivity and mass control. The counterexamples of the Michel Pierre and Didier Schmidt show now that for any super quadratic exponent, you find a sufficiently large space dimension that system which is positive in the mass dissipate if you have finite time L infinity blowout. And note that all of these solutions which are blowing up here, they are global in time weak solutions. So this is really basically where global classical solution are breaking down by global weak solution persisting, right? This is still in the framework where we have shown global weak solutions in some sense. So this is sort of the state of the art of the existence theory, which is somehow getting, you say, to the state where you expected it should be, but it really took, you know, this 19 years or so, more or less, from reviving these questions to sort of being now able to answer many of them. In the interest of time, I will be very brief. That sort of you can do a lot of things for much more general systems than the one I've used as an example. This is really was demonstrated here. There is a way of formalizing reaction diffusion networks, even nonlinear ones. There is a way of defining what is detail balanced and more general complex balance. There is then the consequence of complex balance is that there is still an entropy structure with a nice dissipation functional. And therefore, you can actually show that for all of these systems, you have a convergence to the equilibrium. Even if the systems are such that none of this improved existence theory applies because it's too nonlinear, it might be way more than super quadratic. But you still have the renormalized solutions. Those exist globally. And with those renormalized solutions, you still have convergence to equilibrium, so that all of this modeling is actually somehow meaningful, I would say. Let me just point out that this works if there's not something basically there which is called a boundary equilibrium. While here is an example which is naughty, where you do have something which is called a boundary equilibrium. So this is kind of an equilibrium where some of the species are extinct. So in chemical reactions, also this is possible. You have a thermodynamical degeneracy because at this boundary equilibria, you can check that the entropy dissipation is 0, but the relative entropy to the global equilibrium, which the chemistry should go to, is of course positive. So the entire idea of an entropy dissipation estimate is not possible in full generality. This shows a clear contradiction. If something is so general and nice, you can actually sort of generalize it. You can say that, okay, maybe I don't have a global constant, but maybe I have a constant which is time dependent along solutions. And if the constant is large enough that sort of the time integral is unbounded, then actually you get sort of a moral contradiction. And you dissipate so much entropy on the way to equilibrium that only the right positive equilibrium can be the equilibrium you go to, and it cannot be the boundary equilibrium, because in order to reach the boundary equilibrium, you would need somehow infinite initial entropy, which you of course don't assume for your initial data. So this is the moral story, that for some of these boundary equilibrium systems, you can still generalize the entropy approach. Here it's, for instance, an example where the very terms which are producing the boundary equilibria are also responsible to give you an a priori estimate, which then allows you to argue in our favor without going into any technical treatment. So somehow the terms which produce the boundary equilibria causes the difficulty, gives you an a priori estimate to bypass the difficulty. But this is just for a particular class of systems. There's nothing like a general argument. In particular, this is actually a really, really hard problem, this boundary equilibrium, and I don't want to discuss it here. For instance, this is a problem I think we've looked with Laurent together and Bao the first time maybe 4 or 5 years ago, and still beats us entirely to understand what's going on in this particular complex balance reaction network. So let me finalize and summarize what I wanted to convey to you, that by now, there is really a general existence theory for this particular kind of reaction diffusion systems, not cross diffusion, just classical diagonal reaction diffusion system with mass control. Of course, if you don't have mass control, if you just can grow your mass infinitely, global solutions might be completely out of questions. But mass control is something very general, which you do not only find in chemical reaction networks, you find it in Lotka-Volterra type systems. All of these basically we can sort of apply now a general theorem to this. And in even more general systems, you have an argument of convergence to equilibrium. All it needs so that it allows for renormalized solutions, which you have basically for all complex balance reaction networks. And this is a big part of the chunk of systems that you find, but of course not all of them. These boundary equilibria are still troublesome objects. There is not even fully accepted theory for the ODE systems. There is something which is called the global attractor conjecture. It's formulated for ODEs and not for PDEs, that basically in any general reaction networks, the boundary equilibria sort of there's a more specific notation of it, but they're basically unstable. And in 2015, George Gracian, who is really, a very good mathematician and specialist for the field, published a preprint where he claims that he has proven this global attractor conjecture. But to my knowledge, this paper is not yet appeared. There was a part of a conference devoted to the proof. It doesn't seem to, I don't think that Gracian is, he's a serious mathematician, but it seems that nobody really understands the proof. And I didn't even want to go into the details because it uses methods which are so very different from these kind of concepts we like to work with, that I just didn't want to explore that. So either it's true, then it should be Gracian and co-workers to really out. But I would much rather prefer a different idea to prove that than this kind of theoretical inclusion methods which he uses. And one question, of course, which you always can have in these things is where are the optimal rates and constants, but then we are getting sort of really quite technical. Okay, thank you very much.
Thank you very much, Klemens. So let us go to questions. Kevin, please.
Yes, thank you very much for the talk. So yes, I have a question concerning the counterexample to global existence of solution. Does the counterexample also come from a chemical reaction or not?
No, it doesn't. It has actually sort of a built-in blow-up time. That was already the case for the first counterexample, Michel Piatti-Schmidt. But they used some very first, I think they did it in Maple or so, whatever, algebraic fiddling in order to find constants and coefficients in order to say that for a sufficiently large space dimension, it was something like 10 or 16, you get the counterexample. Now they basically still have the same structure, so it doesn't come out of a classical chemical reaction rate. But in some sense, of course, then it means that if you really go to, let's say, mass action law chemical reaction systems, you can hope for a more general theory. It's an enormous advantage to know already that for certain space dimensions, if the space dimension is large enough, you will not be able to have a very general result based on this positivity preserving and mass control. So
Okay.
this is a very nice result. It was very nice to see that.
Okay, thank you. Thank you.
Thank you, Kevin. There is a question by Virginie. Please, Virginie, switch your camera on and your mic.
Yes, thank you a lot. Thank you very much, Klemens, for this very nice presentation. So I have a question related to the L-infinity norm convergence results that you obtain towards constant equilibria in the reaction diffusion systems that you consider. And my question is also related to cross-diffusion systems that you mentioned in your talk, because some of these systems also share an entropic structure. And then for these systems, you can also prove convergence towards constant equilibrium in L1 norm using entropy dissipation estimate and César-Kullback inequality. So my question is the following. Do you know some cross-diffusion systems for which you can kind of mimic the duality arguments that you mentioned in order to obtain L-infinity bounds, convergence towards?
Yeah. So with cross-diffusion systems, things are much more subtle, right? I mean, basically, one big attempt is to do this transformation to entropy variables, which then Ansgar coined boundedness by entropy kind of. But the transformation has been used way, way before that, right? Before Ansgar wrote that kind of nice skill. So this gives you a different connection. But for instance, SKT, Ariane Trescassès and Laurent have been using quite subtly individual kind of duality estimates for the individual equations in order to have something like bootstrap arguments or general arguments to improve regularity. So even for cross-diffusion problems, this kind of duality methods has been used. But I'm not aware of a general, like, sort of a system-wise viewpoint, right? I mean, I'm not aware of any of that. I don't know, maybe, Laurent, have you seen anything, such general thing? It was always quite specific to the model, how I remember the duality methods being used in cross-diffusion equations.
No, I definitely agree with you. It's rather used for one of the equations of the system rather than for, let's say, a mixture of the equations.
Okay, thank you, Virginie. Thank you, Laurent, too. Are there other questions in the audience? Please raise the hand. Or maybe Laurent, if you want to add some comment, don't hesitate.
No, just thanks a lot.
Okay, so if there is no other question, let us thank again Klemens for his nice talk.